So that's it for Fourier series. No, there are more other things. So it seems like I did a perfect representation of the signal here, but I didn't. I do need the infinite set of vectors of the basis to represent this signal here. There's an interesting phenomenon that happens with signals when there are discontinuities, which is called the Gibbs phenomenon. We can show it. Let me decrease the value of n. Let's go up to 200, not to 100, not 1,000. This oscillation that we see in the borders is called the Gibbs phenomenon. Here. The only way to get rid of this phenomenon is to use the infinite set. So when we were going to 1,000, we didn't see the Gibbs phenomenon because we're not sampling the signal finely enough. If I increase the sampling frequency, that is, if I decrease the sampling period, we will see the Gibbs phenomenon. It will take more time because I have more elements to compute, to exhibit. So the Fourier representation is still the same. I have 1,000 coefficients. The equation to get the coefficients is the same. Now I'm just increasing the sampling period for the signal I am constructing to represent the synthesis. So in the meanwhile, who is this guy Gibbs? Maybe this? Was an American mechanical engineer? Maybe.
Mechanical engineer, would it be?
Fourier. Oh, wow, it's him, the Gibbs phenomenon. He rediscovered the Gibbs phenomenon here, the phenomenon. When there's a discontinuity, there is, here, now we can see it. Then if I decrease the sampling frequency, we cannot see it, but it's there. So I'm coming back to -4 here in the sampling period. It's there, we just don't see it. The only way to get completely rid of it is using infinite coefficients. Now there's one interesting thing. As I vary n, let's see what happens if I get n equal to, oh no. Let's see what happens if I get n equal to 1. 2. N equal to 2, I'm iterating D0, D1 only. This is the signal. It's a sine with an offset. Then if I compute one more, where is it? 3. Then I get 2 sines. We can, yes, we can see the difference because the second harmonic is 0. With 4. 2 signs. With 6, 3 signs. With 6T, something that starts to look like the signal. The more I increase the frequencies, the more I get, the more accurate is my representation. And then there's an interesting relation between the coefficients and the signal in the time domain. So when you did the linear algebra course, was there in the vocabulary the term the energy of a vector? Okay, but there was the norm, right? The norm squared is the energy. We can draw some relations with electrical engineering. So the energy of a signal is the absolute value. I square the absolute value. I integrate this is the energy of a signal, Ex. It's as if I had the signal here, just over 1 ohm resistance. Then if I compute the energy spent here, which is the power integrated in time, then it's voltage squared divided by 1, voltage squared divided by 1. I integrate it over time, I get the energy. So in the end, the energy is the squared norm, because this is the norm, right? The norm of a signal. What's the norm in linear algebra? I do the inner product of the signal with itself, which is to square the signal into sum, and then I have to do the square root. So the norm of the signal is this. So there's the square root here outside. This is the norm, this is the energy. We use this in the signal processing context outside electrical engineering. In any other field, you may find this term, the energy, as the squared norm. It's a measure of information of the signal, and it's also a measure of difference between signals. I measure the energy of the difference of two signals. The higher the energy, the more different they are. But for periodic signals, it's complicated to compute the energy because this integral will not converge, right? I sum this area squared, then that, and that, and that, from minus infinity to infinity. It will not converge. So for periodic signals, we defined the power of a signal, which is, I just divide by the period, and I integrate over one period. Then it's the power. It's the same idea here. I integrate over one period, x of t, absolute value squared. This is the power. What is interesting is that this is also the sum of the absolute value of the coefficients dn or dn squared. dn or dn squared. dn squared. Absolute value of dn squared. So this is a way we can use to measure how close I am to my original signal if I am truncating the Fourier series. Now I'm exhibiting just 120 coefficients from -60 to 60. So I created here another plot. Look what I'm doing here. I created a vector P, which is the absolute value of D squared. Then I am doubling it because D only has, I'm only computing D for positive, for non-negative n, right? So I'm doubling the value. Then I do the cumulative sum, and then what I get is as a result is this. So the power of the signal as a function of n, n being how much I am truncating the signal. So I'm doing an approximation, x hat, which goes from minus n, big N, to plus big N. So how much this approximation is close to the actual signal? Well, we can see that this is approaching half asymptotically, right? So if we compute the power here, we will get half, because the power is 1 over 0.1, then this will give 1, this will give half, so 10, not half, this will give 0.05, then times 10 will be half. So how much am I approaching half? We can also do this. We can divide it by half. Then it approaches 1. We can do this. Then we have a measure of the error, right? If I do this, this is a percentage of how much I am close to the signal. Here, with just one coefficient, I'm already above 90%. With just the constant term and the first coefficient, I already have more than 90% of the signal. Then we can do a log scale here. If we do the difference, here we can see that less than 10% error. We can do the difference and do a semi-log y. Yes, with n equal to 20, I have 99% of the signal. And so on. So I created this plot just to show you more or less how the things evolve. Seems like no one's watching it because I was not displaying the screen and no one complained. So this is called the Parseval's relation. This is Parseval's relation, or Parseval's theorem, which is a generalization of the Pythagorean theorem. You square each axis and you have the total squared, right? This squared plus this squared equals this squared.
The relation is the relation between the time domain and frequency domain way of computing the power.
Yes, this is the way of computing the power. This is the Parseval's relation, the fact that this integral equals this summation. And we can see it as a generalization of the Pythagorean theorem because we're taking each, the value, the length of each component in each axis, we're squaring them, and the result is the total distance squared, being distance the norm.
Just out of curiosity, this concept of energy and power, what would be a good application of real life?
Exactly this, measuring the difference, how close we are to a certain signal when we do an approximate representation. How similar signals are.
Suppose you have a signal X and Y. You would divide them and compute the energy of the
you would compute the energy or power of the difference. That's what we do when we compare signals. We do the norm of the difference. It's just the square root of the norm is the square root of the power. Here I'm formulating in terms of power because this is how this theorem works. It's how the Pythagorean theorem works as well. Things are powered, are squared. Things are squared. Now we can take advantage of all properties of exponentials because we are representing any signal as a composition of exponentials. In the first class, we've seen that they are eigenfunctions to some operations. Which operations?
I think we saw the exponential is the eigenfunction of derivative.
Of derivative is one operation. So the derivative, time derivative of e to the j omega, some omega 0 t, might be e to the j omega 0 t times something, meaning that it is an eigenfunction for this operation. In fact, it is 1 over, for derivative, no, for derivative, it's j omega 0 times e to the j omega 0 t. So this is the eigenvalue associated with this eigenfunction. So taking the derivative is simple for this kind of signal. You just multiply by the argument that's multiplying t. Then, if x of t is this, what is the derivative of x of t? You just apply the derivative in all of them. So you still have the sum here from minus infinity to infinity of n. You have the dn, and you just have to put here j n omega 0. J n omega 0. E to the j n omega 0 t. So if this signal is periodic with a fundamental frequency omega 0, and it has these Fourier series coefficients, then its time domain derivative is also periodic with a fundamental frequency omega 0, and its Fourier series coefficients are these. You just take each coefficient and you multiply by j and omega 0. So let's do it. It's what I'm doing here. Here. So I'm taking each coefficient. Yes. I'm calling it Cn. Oh, here, yes. D is my array of coefficients dn, then I'm multiplying by j n omega 0. Control enter. Here it is. Not beautiful because of the Gibbs phenomenon. What do I have as n? 1000. What do I have as TS? No, it's here, 1000. Now, yes. This. Here, time domain derivative. Does it make any sense?
Professor, the screen again.
Ah, okay. There. So what I'm doing is I am multiplying each coefficient dn by 1j n omega 0. And then I'm plotting, I'm casting the signal as the Fourier series sum here. I'm calling it y of t. And here's the result. Is this the derivative of this? Yes. Here, the derivative might be the Dirac delta, right? Then it might tend to infinity. So this value will actually depend on how many exponentials I am summing. But if I sum all of them, it should go up to infinity. So this is when I have an uprising edge. This is when I have a down falling edge, and so on. So it works. What I did in the end of the day is I provided an equation for the computation of the coefficients. Then I just multiplied each coefficient by this, and I summed the signal using the Fourier series. So we saw the Parseval's relation for this example. We took advantage of the fact that these guys are eigenfunctions for the derivative. Now the next topic is the time shift property, which is also very useful and very interesting for who studies visual displacement. That's where the phase correlation algorithms come from. So, let's show that exponentials are also eigenfunctions for another operation, which is time shifting. If you have an x of t, e to the j omega 0 t, then what is x of t minus t0? Well, I just have to substitute t for t0 here. So if I shift the signal, if I shift the exponential, I will have a shifted exponential. J omega 0 t minus t0. I'm shifting the signal in t0 seconds to the right. So there's this property of the exponents, which is I can do e to the j omega 0 t times e to the minus j omega 0 t0. E to the j omega 0 t, which is the original exponential, so it happened again. E to the minus j omega 0 t0, which is not a function of t, then it's a scalar, it's a constant. So this is an eigenfunction for this operation of time shift. You just multiply it by e to the minus j omega 0 t0. This will give you a complex number with magnitude 1 and with the phase. The phase will be larger when t0 is larger, also when omega 0 is larger. So we can create a phased version of this signal. It's centered in 0. Let's make it centered somewhere else. Where do you want to make it centered? This is 0.25. 0.025, sorry. 0.05, it will be centered here, so it will be half a period. That's a good guess. So I had 0.7 here, so let's go 0.5. So the shifted coefficients are just the original coefficients multiplied by minus j and omega 0 t, because I can extend this property to the Fourier series, then if I have x of t as a Fourier summation, e to the j n omega 0 t, I just have to multiply here this. J n omega 0. Then I will have the coefficients of the shifted signal. J n omega 0.
Será que morreu de novo o notebook?
Acho que foi alguma coisa assim, pô. Tá travadão, né? Tentei entrar de volta aqui. Não.
Voltou.
Vamos ver se ele ia ver a gente.
Aí. So, can you hear me now?
Yep.
Was it just the sound or something else that stopped working?
Your sound and your screen was frozen.
Ah, okay. Now it's
No, I think it's okay.
okay. Thank you. Yes. So the shifted signal here, centered at 0.5. It's as simple as that. And derivative property, time shift property. We can also avoid convolution, because convolution, maybe you remember that convolution with something, with anything, is another operation for which exponentials are eigenfunctions. Right? So in the video that I posted maybe yesterday, what made possible that we defined frequency response was that e to the j omega 0 t convolved with some impulse response can be written like that. The same function, then what? Times the frequency response at this frequency. So again, we avoid some complicated operation because it's an eigenfunction. We just have to find the frequency response. And I have an example here. So the example is about, well, so before the example, what happens if I have an x of t, which is periodical, which is periodic, convolved with some age of t. If this is periodic, I can write it as a Fourier series. The n e to the j n omega 0 t. This convolved with age of t, but I can convolve with each individual exponential. Then, no convolution needed if the signal is periodic. The n frequency response at this frequency, e to the j n omega 0 t. So you have a periodic signal convolved with some function. You just find the frequency response, considering that this is an impulse response. You just find the frequency response and you get the coefficients for the result of the convolution. Another interesting property that's here to ease our lives. Then let's go to an example with an RC circuit. I have a circuit where my x of t is a voltage source. Then I have a resistance of 2 ohms, capacitance of 0.1 farad, and the output is defined as the voltage over the resistor. This is the output. We can find the frequency response using the transformed circuit with phasors, right? The frequency response of this circuit is, well, to help those who did not study circuits, how do we do this? When everything is in series here, this goes in the numerator, and the sum of everything goes in the denominator, right? The sum of the impedances. What's the impedance of the resistor? It's the resistance itself. And here I have to do the sum. So the impedance of the resistor plus the impedance of the capacitor. What's the impedance of the capacitor? 1 over j omega c. If I had an inductor with inductance L, what would be the impedance? J omega L. So if you didn't study electric circuits, this is how we cast the frequency response of what we call impedance divider. You take where the output is measured and put here, and you put the sum of everything else here. And this is the impedance of resistors, this is the impedance of capacitors, this is the impedance of inductors. So if I put this here, I could find the impulse response and do the convolution with the impulse response. Now, do we know how to compute, how to find impulse responses? We still don't know. When we study the Fourier transform and the Laplace transform, then we will know. But for electrical circuits, we know how to compute the frequency response right from the circuit diagram. So I could do the convolution, but I can avoid the convolution and just take the coefficients and multiply by this. I just put the n omega 0 here. This is what's happening in this cell here. I created a vector j omega just to simplify the notation here. So the frequency response is here. Well, j omega is j times n omega 0, which are the frequencies that I am interested in. So r times r plus 1 over j omega rc. To avoid division by 0, here I would have a division by 0, right? For frequency 0, this guy would be infinite. For frequency 0, no, this guy would be 0. This guy would be infinite. If this guy is infinite, this is 0. So for frequency 0, to avoid division by 0, I'm telling the script that the frequency response for 0 is 0. Then I take my coefficients and just multiply by the frequency response. And I cast the Fourier series again, and here's the result. Let's change the capacitor. Let's put a smaller capacitor here, -2. Better now, -3. Now it looks like what I get here, right? In the rising edge, the current starts to flow to charge the capacitor, and then it decays to 0. Then with the falling edge, again, the current flows in this direction, and it decays to 0. This is a low pass or high pass filter. What I'm seeing are high frequencies or low frequencies. This signal changes faster than this one or not? Yes, it's faster. It goes to 0. It goes to 1 and back to 0 faster. So this is a high pass filter. The low pass filter is over here. With the low pass filter, I will not see things change rapidly. I will not see this. I will not see discontinuities. We can change the function here. Here's what we see over the capacitor. So it's a low pass. When there's a rising edge, it does not rise immediately. It goes with an upgoing asymptotical curve. That's it. Circuit simulation with the Fourier series. So we just multiply each coefficient by the frequency response. That's it. That's it for Fourier series. We can go to the next